Hey, so one of the things I want to talk about is just uh, kind of the idea of the normal distribution and statistical significance testing, and what that means for us, right? So everything that we do in terms of statistical significance is based on the normal distribution, right? And the normal distribution, it's such a beautiful thing that occurs in nature for so many of our variables. It looks like this, right? And you learned a little bit about this during week 2. The normal distribution is one where the mean, the median, and the mode are all exactly the same number, right? That it's perfectly mesocurtic, which means it's not too peaked, it's not too flat, it's just like perfectly right in between. It's kind of Goldilocks. It's not skewed, which is to say it's symmetrical. The left side and the right side are just the same as each other, and that's the normal distribution. And what's nice about the normal distribution is that along with that comes some facts. In particular, the idea that 68% of the population, or 68% of our sample, or 68% of whatever is within the normal distribution as a frequency distribution, is within one standard deviation of the mean, right? So this is a histogram. This is how the frequency density, so how many people are in any particular level, and these are all levels of one particular variable, right? So it's just a histogram. And it centers around the mean of the group, the mean of the population, etc. And what we know is that 68% of everybody are within one standard deviation, plus or minus, of the mean. 95% are within 2 standard deviations of the mean. And 99% are within 3 standard deviations of the mean, which means if you're more than 3 standard deviations away from the mean, so for instance, let's say that you are, say, above 3.5 standard deviations of the mean, which means you have a z-score of 3 or greater when you are at least 3 standard deviations away from the mean. That means that you are a very extreme case. You are only in 1% of the population. And so we're willing to say, you might be from a different population, or you might be from a different sample, or you're a very extreme case. And that's really what it comes down to then when we do our statistical significance testing. A z-test is looking at a one person, are they different from the population? We'd say, well, if they're pretty close to 0, right, or very close to the mean for the population, right? So if we take height, right, are you pretty close to the mean height of everyone else? If so, you're probably the same as everybody else. If, on the other hand, you are exceedingly tall, if you're 100 feet tall, we might say, there's something going on there, something systematic. This isn't just chance. There's something weird happening here if you're 100 feet tall. Okay, so somewhere between 0, right, being exactly at the average height, which is, 5 foot something, 5'6" or something like that. Something between no difference from the mean and 100 feet greater than everyone else, somewhere in between those two is our decision point for saying you are different in some way, right? Or to say that this person or this case is different in some way. It is so extremely different from the rest of the population by using the mean by comparison that there's something going on here. And the question for us then as data scientists is, how extreme is too extreme? And the answer that we've come to, that we kind of all agree on, is if there's only a 5% chance that we would get this extreme score, if there was in fact no difference, that's probably too extreme, right? And so if we are at least 2 standard deviations away, then we are very extreme, and we're willing to say that probably comes from a different population. So that's the z-test. The t-test, same thing, a one-sample t-test. We're comparing our sample to the general population. And we're saying on a particular variable, if the mean for our sample is so different from the rest of the population, well, then they're probably some other population that they're in. And how far is too far to say that there's such a big difference? Well, if there's only a 5% chance, or p less than 0.05, if there's only a 5% or less chance that we would have gotten this extreme group mean from if the actual difference was 0, then there's something systematic going on here. Same thing when we look at dependent sample t-tests. If we say before training and after training, you changed so much that there's such an extreme change that we have to say this is more than just this is more than just natural chance, or this is really something happening. Well, how big is that change when we have to start saying something really happened here? Well, the answer is if there was only a 5% chance of getting this change number, if there was in fact no change, then we say that that was extreme. So that's really what this all comes down to, is determining how big of a change, how big of a relationship, how big of a score as compared to a population is so big and so extreme that we're willing to say this is significant. This is a statistically significant difference. And what we agree on is when the probability of getting this extreme score is less than 5%. Now, the probability of getting that if there was no difference, if you were in fact part of the population, if nothing changed, if the relationship was zero, the chances of getting this are 5% or less, then we say there was a systematic difference. That is statistically significant.